Welcome to the Problemers Channel Season 3, Episode 7, the episode which I titled 3 Integers Sort a Discovery, because in this episode we will discover a way to sort 3 integers creatively, that is, without any standard containers, industrial strength, sorting algorithms, and in a smallest number of tests possible. But before we deep dive into the underlying mathematics and computer science of the problem at hand, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit from the material that we present on this channel is for you to go to the home page of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety and follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. And if you have any questions, then by all means do ask. Find an episode that is of interest to you. Use the comment section in that episode and I will find the time to answer all of your questions. The objective of our first computer science problem of Season 3, that is in the problem S3CS1, is to creatively sort 3 integers in the ascending order in such a way that if, for example, the given integers on the input to our creative algorithm are named A, B, C is shown over here, then the integers should be sorted in a way that A is less than or equal to B, which is less than or equal to C. Here I just showed an example of using numbers 1, 2, 3 as a sample. And by the word creative, in this particular challenge, we mean the following. The 3 integers should be sorted without any standard containers, without any popular industrial strength sorting algorithms, and in a smallest number of tests or comparisons across the given integers as possible. And again, as we explained in Season 1, Episode 2, we suggest and recommend that you practice mathematics, physics, and computer science correctly. That means that if you cannot solve this problem completely on your own, then you should not really watch, or for the best results, you should not really watch our presentation in its entirety. Watch only the minimum viable amount of information, and as soon as you catch the whiff of where things going, then we recommend that you put this video on pause, walk away from the computer, and try to carry the solution of this problem on your own all the way to the end from that point onward. Fundamentally, we solve problems in computer science in exactly the same way in which we solve problems in physics and in mathematics. And at first, when we are facing a difficult problem, we want to wrap our brain around the depth of the challenge. We want to understand exactly what is the issue that we have to overcome. And in that case, we usually try to generate a brute force solution. And in this case, the brute force solution amounts to virtually zero intellectual voltage or zero intellectual effort approach, which actually quite straightforward and easy to generate and understand and comprehend as soon as we realize that n distinct items can be arranged in an order sensitive way in a straight line, not in a circular fashion, but in a straight line in n factorial way. In this case, we treat the given integers a, b, c as 3 distinct items. And that means that these 3 distinct items can be arranged in an order sensitive fashion in a straight line in 3 factorial, or 1 times 2 times 3, 6 distinct order sensitive ways. And each such order sensitive arrangement in some sense captured the so-called trichotomy law of real numbers, according to which for any two real numbers x and y, these two numbers participate in exactly and only three relationships. X is less than y, x is equal to y, or x is greater than y. So here we use either one of your favorite industrial strength, the next permutation, linear permutation generating algorithm, or in this case the number of items is quite small. We can do it just on a whim by hand. And here on the top of the board I have written down all 6 order sensitive distinct linear permutations of the items A, B, C. They go as shown on top of the board: A, B, C, B, A, C, B, C, A, C, B, C, A, B, and C, B, A. Once we have the 6 distinct order-sensitive linear arrangements of 3 distinct items on the books, we simply convert all these arrangements, all these permutations into the actionable code by reading the underlying code directly off of each permutation. That is, let's say, take the first permutation, A followed by B followed by C. We craft our first if statement shown over here on top as follows. First, we compare the leftmost or the first element in the triplet against the middle element, and then we compare the middle element of the triplet with the middle component with the rightmost or the last component. We glue these two tests or these two comparisons with an AND operator because we want to ensure that both of these tests succeed, because then this precisely this mechanism will capture this specific permutation and game over. We craft the printf, let's say, statement which says that the first integer is less than or equal to the middle integer, which is less than or equal to the last integer. And here we capture the order of the variables that bind to each formatting specification in exactly the same way in which we have our linear permutation. This is it. This is that straightforward. And once this test succeeds, if this test succeeds, then on the standard out, we will have the integers A, B, C printed in an ascending order, or in such a way that the first integer named A is not larger than the middle integer B, which in turn is not larger than the last integer, the last and the third and the last integer C. And this is it. After that, it's floss, rinse, repeat. For the next if statement, we take the next linear permutation, we do the same thing. We carry out 2 comparisons, the leftmost component against the middle component against the last component, and we put this test into the corresponding if statement as follows. If B is less than or equal to A, B is less than or equal to A, and A is less than or equal to C, A is less than or equal to C, then we craft the corresponding printf statement, which is basically the same thing. The formatting specification will be the same. The only difference will be, again, in what? In the order of the variables. Here the order will be BAC, which precisely captures or faithfully reflects, faithfully depicts the original permutation, which we're converting into the actionable code. And here I use plain English AND for the binary AND operator instead of bringing in more C, let's say, notation for the logical AND, which is double ampersands. We do not need that, but in general this is in pseudo C or C like code that captures all the possible tests that work and service, if you will, each and every linear permutation shown on top of the board, and the game is over. This is all there is to it. How many tests, big tests, we will have? We will have evidently 6 big tests, 1 for each permutation. And what can we say about this algorithm? This algorithm takes 0 intellectual effort to generate. It is straightforward to comprehend. It is very straightforward to code and implement. It is very straightforward to read and understand what is going on, but this code has many issues. I will not delve into all the possible issues from the standpoint of, for example, code duplications. Code duplication, this code is a nightmare. But as far as we're concerned, relating to the topic that was declared in the title of this episode, this algorithm has two fundamental flaws. It is not efficient and it is not scalable. Why is this algorithm not efficient? Put this video on pause, think on your own, you guys tell me, but the answer here is the following. How many tests do we perform per each big, let's say, if statement that services each or converts each and every linear permutation into the actionable code? Well, we execute one test when we compare the leftmost component of the triplet with the middle component, and then we carry out another test when we compare the middle component to the rightmost or the last component in the triplet. So we carry out two tests per permutation in this incarnation of the sorting algorithm. By the corresponding multiplication counting principle, how many tests will we perform overall? Well, in this case, we will have to perform 12 tests. Let's write it down, 12 tests. Write this number down or make a mental note of it. We'll come back to it shortly. And as a hint, it is possible to do actually much better. It is possible to sort 3 integers creatively, not in 12, but in just 3 tests. Think about how. Now, this is as far as non-efficiency of this algorithm is concerned. What does it mean that this algorithm is not scalable? Well, as much as it is easy to comprehend and to generate the next solution of the problem of sorting, let's say 4 integers. What will that sorting algorithm for 4 integers incur? Well, in this case, we will be dealing with quadruplets. Let's say A, B, C, and D. This will be 4 distinct items. We know that 4 distinct items can be arranged in an order-sensitive way in a linear fashion in 4 factorial or 24 different ways. 24 different ways. We will understand what needs to be done. Simply roll through all these permutations. There will be 24 of them. Write them down and convert each linear 4 permutation into the corresponding if statement. You will have how many if statements? Exactly, you will have 24 big if statements. And within each if statement, how many tests will we have? Well, let's think about it. We'll compare these 2 components, then these 2 components, and then these 2 components. This produces how many tests per permutation? 3, exactly. So by the corresponding multiplication counting principle, 24 times 3 comes out to what? A whopping 72 tests. 72 tests. Observe how a minimal increment in the size of the input, stepping from 3 to 4, how that minimal increment in the size of the input into this problem generated an absolutely staggering increase in the amount of work that needs to be done. Stepping from 3 to 4 in terms of input goes 12 to 72 as far as the output, if you will. A whopping 6-fold increase from 12 to 72. 12 times 6 is 72. This is how much more work needs to be done in this case. So this is evidently not scalable. And if we do this analysis for 5 factorial, what will be the deal there? With 5 factorial, we'll have 120. And within each permutation, within each 5 permutation, we'll have to perform 4 tests. 4 times 120, 120 times 4 comes out to another whopping 480 tests. This is evidently not going well for our algorithm, and there is another issue over here which I mostly or basically quietly overlook, but observe this. Despite the fact that we're making 12 tests, in this case in the 3-integer sort, and we will be making 72 tests in the 4-integer test, we will be making a whopping 480 tests for a 5-integer sort. What does our code actually do from the practical standpoint? From the practical standpoint, all our code does is it prints. Listen carefully and let's think about it. It just prints the input integers in the correct order requested in an ascending order. But does it actually sort these integers? Well, on the practical side, this algorithm does not really sort the input in any meaningful way or in a way that can be practical in a real scenario or in a real life situation when we write code, for example, in production environment, let's say. Remember this remark over here that I'm making, because we will come back to it very shortly. And now that we understand that this algorithm is not efficient, it is possible to do better, and it is not scalable, it is time to go back to our problem-solving approaches that we studied in a dedicated manner in Season 1 and Season 2. Recall that on this channel, across a solution to an interesting problem and a story behind how that solution can be developed, the story or a story behind how a solution to a difficult problem can be developed is much more important than the solution itself. Now, to be sure, a solution or the solution to a problem is of course interesting and important, and we want to hear it and we want to know it. But a story, a beautiful, elegant, crisp, creative story behind how that solution was developed is much more interesting and much more important to us. That is, if we can generate and come up with the story, then we definitely can generate a solution as an almost automatic side effect of that creative story. So in this case, how can we sort 3 integers in a creative way that does not use standard containers, does not use popular industrial strength sorting algorithms, and does it better than the brute force zero intellectual effort algorithm that we described in the previous segment? Well, we want to create some sort of context, some material, some vehicle that will allow us to come up with this creative idea. And here, those of our viewers who studied the so-called problem-solving approaches or heuristic templates with us in a dedicated manner across Seasons 1 and Season 2 should be able to come up with the combination of 2 problem-solving approaches shown on the board. That is, reduce and conquer first, and reinterpret and conquer next. Maybe in that particular sequence, maybe not. Remember that to some extent, the well delineated with crisp boundaries, the problem-solving approaches that I explained to you guys across Season 1 and Season 2, in some sense, not very realistic, meaning that in a real environment, in real life, when we're solving real problem, these problem-solving approaches may not be so well delineated, so well have such a crisp boundaries. They can be intermixed or intertwined with each other somehow, and which approach comes to our mind first and which second is also an interesting and a messy point. Sometimes these approaches can come in parallel, sometimes they can come in one after another, but here basically the idea is this. First, let's say the reduce and conquer problem solving approach tells us what? That if we want to solve this or that technical problem using the reduce and conquer problem solving approach, then we should to carry out one step that has two important properties. It reduces the size or the perceived complexity of the given problem on the one hand. On the other hand, it preserves the technical essence of the original larger or more complex problem. And in this case, what can be a faithful reduced in size copy of the given problem? Well, a faithful reduced in size copy of the original problem is the problem of sorting two integers, because 0 integers is evidently no work, 1 integer is sorted by default. So the next sweet spot between doesn't make any sense or not interesting versus difficult right now is what? Is the two integer problem. So how can we sort two integers creatively in a way that will alleviate us from all the problems of the algorithm that we looked at in the previous section? Well, here, this is where the second problem-solving approach comes in, reinterpret and conquer. And those of our viewers who studied these approaches with us in a dedicated manner across seasons 1 and 2 remember that according to the reinterpret and conquer problem-solving approach, we want to come up with a different interpretation or reinterpretation of the original material in the given problem. That is both. It has the following two properties that provides us with a tactical advantage, or that reinterpretation makes the search for a solution or the process of generating that solution more tractable. And second, just like in the reduce and conquer, we want to do what? Well, the reinterpreted material has to bring with it, has to conserve, if you will, or preserve the technical essence of the current standing problem, because we want to solve this problem and not some other problem. So what fruitful reinterpretation of the given problem we can come up with that will help us solve the given problem creatively. Here, all people are wired differently, hopefully, and this is a good thing. Different people think in different ways. This is not the only way. This is just my way, for example, my suggestion, because my mind is burdened with all the coin weighing problems that I solved in my problem-solving career. And here my suggestion is that we bring in the coin weighing problem as an analogy or as a fruitful reinterpretation of the given problem to make things less abstract and give us something tangible to latch on and use as a fodder for, or use as a bridge for connecting the two problems. So hopefully in the land of coin weighing problems, the situation will be more revealing or more suggestive. So here the question is, so by reinterpreting the reduced or faithfully reduced in size original problem, we pose the following question. Given two coins, one properly functioning set of pen scales, how can we sort two coins by mass in the smallest number of weighings? And why is that? Well, because in this reinterpretation, remember, we need to establish the correlation or a mapping, if you will. So in this reinterpretation of the original problem, we correlate a coin to an integer and an integer to a coin. And we correlate a weighing, one weighing on the properly functioning set of pen scales with a, let's say, less than or equal to test, and conversely, and less than or equal to test across two integers, we correlate to a single weighing on the properly functioning set of pen scales. And here we remember that in this case there are only three possible outcomes of any one single weighing on the set of pen scales. The scales balance. So if we name, for example, this pen as left, with designated with letter L, this pen we name right, we designate it with R. The fact that the experimental fact that pen scales balance, we capture algebraically with L equal to R. The second outcome that's possible in this case is when the left pen goes up and the right pen goes down. We capture this experimental result in the world of weighing coins algebraically as L is strictly less than R. And the third and the final outcome in this case of a single weighing could be what? The left pen goes down while the right pen goes up. We capture this experimental result algebraically with L greater than R. Again, these three algebraic results, if you will, or these three outcomes of a coin weighing problem correspond to what? Exactly to the previously mentioned trichotomy law of real numbers. Given any two real numbers, such as, for example, L and R, these two numbers are locked into precisely and only three relationships captured algebraically as follows. Two numbers are equal, one is less than the other, or one is larger than the other. So now once we inhale all this material, reduce and conquer, faithfully reduce and conquer, faithfully reinterpret and conquer, coins, weighings, pen scales, how can we solve the problem of sorting two coins by mass using one properly functioning set of pen scales with a minimal number of weighings? Well, looking at the description of the possible outcomes, one solution or a solution that instantly comes to mind is the following. We put the coin A, let's say, on the left pen. We put the coin B on the right pen. Then we perform one weighing. And then we observe the outcomes. So here, to make things slightly more interesting, let's say we wrap this whole experiment into a game. Someone hands us two coins and says, here, sort these two coins by mass, but we are allowed to communicate the result of our sorting, if you will, not verbally. In other words, we cannot speak, but we only can communicate the result of our sorting process, if you will, algebraically by naming the coins in such a way that once we give back the coin named A, it will be not heavier than the coin that is named B. Thus, the situation here unfolds in the following way. Someone gives us two coins. We cannot speak the result of sorting back. We have to give the coins back with the proper names. And we name one coin A. We put it, let's say, on the left pen. We name the remaining coin B. We put it, let's say, on the right pen. It doesn't matter. We can put them on different pens. We perform one weighing and we observe the results. If the pens balance, so if the pens balance, in other words, if A is equal to B, they have equal mass, then the names of the coins that we wrote on them before we started this experiment, do they match this requirement of sorting these coins by mass in an ascending order? The answer is yes, they do. So we simply return the coins. So here we return the coins. A less than or equal to B. So in this case, the coin A is not heavier than the coin B. The requirement stands. We simply write down the names, perform the experiment, and hand over the coins, and someone looks at them and says, great, A is not heavier than B. So these two coins are sorted by mass in an ascending order. Wonderful. What if the pen on which the coin A is sitting right now goes up as a second result of our experiment? Well, in this case, A will be strictly less than B. And what does that mean? Well, that means that actual relationship honors the requirement that the two coins are sorted by mass in an ascending order, because it is the case that A is not heavier than B. Wonderful. Now comes the interesting part, and this is where the discovery is awaiting for us. If the coin where the coin named A, whatever pen it is on, goes down, and the other pen with the remaining coin goes up. What does that mean? That means that A is actually heavier than B. And then what do we do in this case? Remember the rule of this game. We cannot tell the person to whom we are returning the sorted coins, if you will, or whether they're sorted or not. That is not really clear. We can say, hey, listen, I named this coin A, so it is actually heavier than the coin B. So what do we do? How do we communicate the result of our sorting back to whoever gave us the coins in such a way that we cannot actually speak, we cannot utter the word, but we have to honor this requirement. How can this be done? Think on your own, put this video on pause, walk away, and then compare your idea to ours when you generate one. When we witness the result of, or when we witness the outcome of our experiment that violates the requested ascending sort order of the coins by mass, then what do we do? Well, the bright idea that you are expected to generate on your own, and the idea towards which we are driving all this time, and if you generated that idea by different means, then definitely we want to hear from you. Share your idea and your fodder, your material, your device that you used in order to generate that idea with us in the comment section. What we do is what is easy or what is very permissible to do in this particular context. And in this particular context, what is easy or very permissible to do? Well, it is very easy in some sense to name the coin or any coins any which way we like. It was very easy to name the one coin as A and the other coin as B. And let's think about it for a moment. When we did so, when we named one coin A and we named the other coin B, what did we go by? Nothing really. We did it on a whim. In some sense, it was a random event, if you will. We put our coins in the bag, we shook them well, we pulled out the first coin, whatever it was, we wrote A on it, but we could have written B on it just as well. We yanked out the second coin and we wrote the remaining name on it. There was no real meaning, half depth, or weight, if you will, attached to the naming process, so that is easy. So if we named our coins as A and B on the whim, and in this particular experiment we witnessed the result that violates the requested order, the ascending order of sorting these coins, then what do? Well, we simply rename the coins before we return them, because that is easy to do. But this is, in a way, a creative solution. It is a clever maneuver, and it solves the given problem. Look at this. If A is greater than B, if we put our coins on the properly functioning set of pen scale and the coin with the name A went down, it means it's heavier. What do? Well, we erase A on that coin. Then we erase A on that coin and we rename it as B. We take the other coin that was used to be named B. We erase the name B on it and we write A on it. We write A on it. So now the heavier coin is actually named what? B. Now the sorting requirement is satisfied, and what do before we return these coins? After we rename it, and then we do what? Then we return, and then we return A is not heavier than B. Problem solved. This is the bright idea which you are expected to generate on your own, and that is test. Let's give it a compact name that captures the technical essence of what just happened. Test and rename if needed. And when is it needed to rename our coins? Well, when the coin that we, let's say, logically, collectively agreed to call the first or the leftmost component in our set of two coins turned out to be heavier than the other one in this case. So test and rename if needed, and then return the coins that are already sorted properly by mass in an ascending order, and the game is over. And now based on the or according to the reinterpret and conquer problem solving approach. Once we solve the problem with the reinterpreted material, we bring it back and try to see what does it mean in the context of the original problem. So renaming coins in the coin weighing problem corresponds to what maneuver in the world of integers? Well, there could be several things. At the very last episode, I'll show you guys a professional way of doing these things by working with the uh, pointer to a pointer. But this will be extra for experts. Do not worry about it for now. That means that the act of renaming coins in the coin weighing world corresponds to swapping the values. For example, that's not the only way, but for now, for clarity and demonstration purposes, that translates back to swapping the values that sit in the integers a and b. We put the value that used to be in a into the integer named b, and we put the value that used to be in the integer named b into the value that sits in the integer named a, and effectively this is it. The problem of sorting two integers creatively is solved. As a side remark, note that the success of a reinterpretation or the success of your reinterpretation model can be measured on how organically it intertwines or splices into or mixes with the original material. For example, in the official academic setting, such an organic model of, for example, complex numbers are the corresponding points in the complex plane. And even though technically and pedantically a number is not a geometric point and a geometric point is not a number, this reinterpretation or interpretation of one object in terms of the other is so natural, is so organic that once we understand what is going on, we begin mixing or using the two objects, two very distinct mathematical objects, interchangeably. So here again, in my mind, and maybe I am biased, correct me if I'm wrong, see what you think, maybe you have a different model, but in my mind, in this particular context, coins and integers intermix very organically, very naturally, and you, in your mind, you start mixing the two and using the two objects interchangeably. You see a coin, you think an integer, you think an integer, you see a coin, weighing, comparison, this and that. All this happy mess is helpful and creative, and good things happen. In any case, all the actionable source code to this episode is available in the free PDF file in my public GitHub repository. Don't worry about any of this code. The link to that free PDF file, to the free GitHub repository of mine, is in the comment section. Look for it, click on it, download, go to town with experimenting with this solution. And again, I showed the solutions and all the sample code, actionable code to this episode available in the free PDF file. I wrote and tested using the best programming language of all times, that is C, of course. If you have any other programming language in mind, do it in your way. But here we will look at this solution piecemeal. First is remember from the previous segment, the act of renaming coins if needed. So test and rename, reinterpret it back into the world of integer sorting and integer comparison in the one way. It's not the only, but a way. In the last segment, I'll show a different way of doing these things. Here, this reinterpreted way goes back to test and swap. So swapping the values that sit into integers x and y in C can be done as follows. The function returns void. We name it swap. Technically, if you want to be pedantic, you can call it swap integers or swap I, swap ins, whatever. The choice is yours. Your imagination is the limit. But here, fundamentally, we take two arguments as input, pointers to integer x and integer y. We create a temporary variable where we store the value of, let's say, x. You can do y if you want. And then we perform the interchange again. It doesn't really matter. All these clever tricks with XOR, bit flipping, bit shifting, it's irrelevant. It obscures the point. The idea is that we swap. In the integer named x, we store the value that is in the integer y, and once we lose it, once this value is gone, we go back to the variable called temp, and from the temp we write the value to the address location that is named by the integer y. This way the values in the integers x and y are swapped. Game over, and we can move on to the actual sorting algorithm. Converting the result of the solution of our reinterpreted problem back into a solution of the original problem, we obtain another function that returns void. I named it sort A for sort in an ascending order, A for ascending. If you were to do the same thing, if you were to sort these integers in a descending order, you'll probably name it sort D for descending. It doesn't really matter. But here the fundamental idea is the following. The version that you see over here is algorithmically correct. It is a faithful rendition of our reinterpreted of the solution of the reinterpreted problem, but it is still impractical because it doesn't really sort the integers a and b. These two integers are passed into this function by value, not by address. So the test that we perform over here, if a is greater than b, remember this is the case when the pan with the coin named A went down, meaning that the coin named A is heavier, or by value the integer A is larger than B. Then we perform this swap by passing the addresses of the variables A and B that you saw in the previous segment. This change that is applied, possibly applied to the values that stored in the integers A and B, only is a short-lived. It only lives for the duration of the scope designated by these two squigglies, and after that it is gone. The change will not be reflected outside, and we will look at the practical version next. But here basically the idea is this: compare and swap if needed, test and swap, compare and swap if needed. This is in some sense the name of our algorithm. This is a creative solution. Here, observe that even though this is a silly way of doing things, but our printf with the formatting specification written here and the arguments listed after it, A binds to this specification, B binds to this specification. This specification in some sense, observe, remains one and the same. If there was no swap and this test failed, then our integers will still come out honoring the ascending order of sorting these two integers. And if the test succeeds, meaning the integer A by value is larger than B, then the swap will make things right, and one and the same statement holds. And again, next I'll show a version of the same sorting function that is both algorithmically correct and is practical. In order to make our sorting function much more practical and realistic and usable in a production environment, all we do is we go back to it and change its signature by taking, instead of actual integers, the addresses or pointers to the integers, let's say A and B. In that case, our test changes slightly. Before we test, we dereference. And this is how we do it: star A larger than star B. And if that is the case, if this test succeeds, then we do a swap. But in this case, pay attention, instead of passing addresses, we're actually passing A and B as the variables, because A and B are precisely the addresses of integers, and this is precisely what our swap function expects. And now observe that this more with both algorithmically correct and practical function became shorter or smaller, less number of codes is needed. The printf statement that you saw the second ago at the bottom of our function is gone, because now the changes that are made to the content of the variables A and B will be visible outside that function. And again, do not worry, I will provide the source code that is actionable, that you can compile, test, run, play with, modify at will. It is available in the free PDF file in the comment section to that episode. But now we will move on to the next step, because now that we solved the faithfully reduced problem of sorting 2 coins, we can step up back to the original problem, precisely as the reduce and conquer problem solving approach prescribes. Because remember, once we descended, if you will, down the perceived ladder of complexity to the simplest possible problem that we can solve, we now use the tactical knowledge, the material that we developed and discovered while solving the simplest problem. Now we rely on it, and using it as the fodder, we step up and we try to solve the next more difficult problem that is related. And the next more difficult problem is precisely the problem of sorting 3 integers creatively. Now that we solved creatively the problem of sorting 2 integers, we step up our perceived level of complexity of this problem, and according to the reduce and conquer problem solving approach, we try to inhale all the technical knowledge and the technical devices that we discovered during the solution of the reduced in size or reduced in complexity problem, and apply it to the solution, or to the process of generating the solution for the next increased in size problem. And in this case, what does that mean? Well, in this case, it means that we are given, let's say, 3 coins, if you will, named A, B, and C, and we have to play the same game. Someone gives us 3 coins and asks us to return these coins sorted by mass in an ascending order, in such a way that the coin A is not heavier than the coin B, and the coin B is not heavier than the coin C. Again, this is all folds nicely into our idea of using coins and integers interchangeably. We say one thing, we mean the other, and we say the other, we mean the first thing. Integers, coins, weighing, test, comparison. So this is all beautiful stuff. How do we do it? How do we solve this problem? Well, we go back to the way we did things in mathematics, and here in computer science, we pretty much do the same thing. When we're given the problem of size 3, we first solve the similar problem of size 2. You see, this is the idea, and this is how things work in mathematics, and that's how they travel outside of mathematics into computer science. So here, we take 2 coins and we sort them by mass in an ascending order creatively, using the previously discovered algorithm. And in that case, what will happen? In that case, after that sort is done, our coins will be sorted in the following way. The coin that has name A, which possibly maybe was the coin B before that, now it is less than or equal to the coin named B by mass, or our integers A and B are sorted that way. This is what we do. This is what you guys see on the right hand side of your screen. I already wired all the needed information in for the function sort A, sort ascending. It takes 3 arguments, 3 pointers to the integers named A, B, and C. In this code right here, if star A greater than star B, swap A and B, precisely corresponds to that act of solving a faithfully reduced copy of the problem, sorting 2 coins. So now here we sorted 2 coins. So now the last step, we need to place the coin C correctly, and the coin C can be placed where? Well, we do not know. It can be placed to the left of A because it can be still lighter than the coin A. It can go to the right of the coin B because it can so happen that it is heavier than the coin B. And it can also so happen that C is heavier than A, but it is lighter than B. So it will be sitting somewhere over here. And if that is the case, then precisely we do what we will have. What we will have our sorting order honored, the ascending sorting order honored, if we do what? Well, here is another beautiful thing that mathematics gifts us and brings it to the world of computer science or physics, for example. The way we solve this smaller problem of sorting 2 integers, we can solve the problem that is larger, sorting 3 integers, because now the act of placing the coin named C or the integer named C correctly in order to honor the requested sorting order, ascending or descending, whatever the case may be, can be done using exactly the same test and swap idea. Once the discovery is made, we can use, reuse, and abuse it in a good way. And that is the essence of the reduce and conquer problem solving approach. Gather or inhale the tactical material gathered in the solution of the simpler or smaller problem and bring it into the solution of the more difficult problem. What was the tactical device that we discovered while solving this simpler or smaller, reduced in size, faithfully reduced in size problem? Well, it was the test and rename if needed. So here, by testing C against A, we can do what? Test and rename. And by testing C against B, we can do what? We can also test and rename if needed. So when we test the coin C against the coin A, if it so happened that the coin A is heavier than C, then what should we do? Well, we should swap the values that sit in this integer. So here the second test will be if, I'll use the same chalk, if the value that sits in the integer A happens to be A larger than the value that sits in the integer named C. You see, we do this exactly the same thing that we did discovered in the faithfully reduced in size problem. We swap the integers, the values in the integers A and C. This is done. And when we test the integer C, or when we test the mass of the coin C against the mass of the coin B, or the value of the integer C against the value of the integer B, if the integer B happens to be larger than C, C really belongs where? To the right of B, because our order, the target order, which we want to ensure that is the case once we're done with our sorting algorithm, is precisely that. So if it so happened that B is heavier than C, the coin named B is heavier than the coin named C, what do? We rename the coins, or in the world of integers, we swap the values that sit in these integers. Look at this. So now the third test will be if the value that sits in the integer named B is larger than the value that sits in the integer named C. Then we swap B and C, and the game is over. This is all there is to it. This, in some sense, our original 3-integer sorting problem is solved creatively without using any containers, without using any industrial strength sorting algorithms. And by the looks of it, we managed to solve this problem in exactly 3 tests. Look at how many comparisons do we make. Let's count 1, 2, and 3. And in some sense, we weighed our coins. All the coins went on the pens. Every integer participated in the test. The value of each integer was probed. And by the looks of it, what beautiful symmetry do we see over here? Well, in this algorithm, the value of each integer was actually probed twice. A, star A and star A over here, that's twice. Star B and star B over here, that's twice. And star C and star C over here, that is also twice. Game over, problem solved. And in order to see this algorithm in action, let us carry out the following computation. For a sample computation, let us assume that the input into our creative three-integer sorting algorithm is the following. The integer A carries the initial value of 9, the integer B carries the initial value of 7, the integer C carries the initial value of 5, and on the output we expect our algorithm to produce the numbers in the following way. A should be 5, B should be what? 7, and C should be 9. So 5, 7, 9 is the expected order. So now we want to see how the numbers will dance around according to our algorithm. Our first step over here, the first if statement, says what? If the value in A is greater than the value in B. 9 and 7. Is 9 greater than 7? Yes, it is. 9 is greater than 7. So what do we do then? Over here, we swap A and B. So here in A goes 7, in B goes 9, and 5 stays in C. So far, so good. So if we reflect, well, let's do the computation first. So after the first test shown over here, this is the state of variable so far. The next test in our algorithm is A against C. So what do we have now in A? Don't forget, the value is updated over here in each current row. 7 versus 5. Is 7 larger than 5? Yes, it is. So what do? We swap A and C, the values that sit in A and C. So here 5 goes into A, 5, 7 goes into C, 7, and 9 stays put. Here is 9. So this is the state of affairs after the second test. Now we still have the third test to execute. In the third test, we pit B against C. So now we compare B against C. Is 9 greater than 7? Yes, it is greater. 9 is greater than 7. The test succeeds. We jump into swap. We swap B and C. Swap B and C. So 9 jumps into C. 9, C jumps into B. 7, jumps into B. And 5 percolates down as it was. No one is acting on it. Game over. So now if we reflect our dancing, our dance of numbers with the corresponding arrows, I will do that for a reason. And this is quite natural when we trace the time evolution of our algorithm and see how the numbers play out. This is pretty much almost guaranteed that that is what we will do in order to understand what's going on. So in the first test, we put this value here, and I use blue, we put this value over here. 9 came over here, 5 percolated down, if you will. We can put the green arrow like this. Now from the first to the second test, what happened? Well, look at this. 9 percolated down as it is. So then 7 jumped over here, and 5 jumped, I'm sorry, I used the wrong color. Here is yellow is this, and then green is this. 5 jumped over here. And for the last test, what happened? Well, blue 5 percolated down as is. The 9 went here, the number 9, and the number 7, which was green for C, went over here, and we are done. Now that we understand what is going on, how this algorithm works, another interesting question is why it works correctly and why we claim it works correctly, and how to generate a proof that our algorithm is indeed correct, and no matter what the permutation of inputs are, or no matter what these permutations are, it will always produce a sorted set of three integers on the output correctly in the ascending order. That is a different story, but in order to see, inhale the whole thing, to have a bird's eye view on how the whole thing is orchestrated together in a usable, remember, this is both algorithmically correct and practically, because now changes that are inflicted onto the variables a, b, and c will be visible outside that function. So altogether, here is how a sample code may look like. Of course, you can do this task any which way you like. You can arrange the code in a different manner. Be my guest. You can use a different programming language, but to give you a coherent view of how this whole thing can be used in the practical setting, here is a sample code I showed on the left-hand side of your screen. And again, do not worry, all the actionable code that is readily compilable and testable is in the free PDF file that sits in my GitHub repo. The link to that free PDF file in the comments section. Please be my guest. Click download. You can see the code. There is nothing malicious going on. Everything is right there, very transparent and self-explanatory. But for example, once we understand how the sort A algorithm works for three integers, that's shown over here on the right hand side of your screen, we open up a file, let's say called sort3int.c. We save this code in that file. We implement our swap function. You remember from a couple segments ago, swap. Type in swap, type in sort. Sort is right here. Organize the main function, int argc, char star argv arrow, extern int. I omit all these details. You can see them again in this free PDF file. Be my guest. The idea here is the following. We create three frame variables, three stack frame variables named A, B, and C. We take them in from the command line via ASCII to I. This is a standard C runtime library function, A to I, argv sub 1, argv sub 2, argv sub 3 for three variables. Take them in from the command line, print the numbers before we sorted, and now we execute the sort. Here there's the call to that sort function, except that in my implementation that you will see in the free PDF file, in addition to all these things, I made the sort a function. Here you can see it returns void, but in my code it returns size t for the number of swaps that were performed by the sorting algorithm. All you do here is, again, the adjustment is trivial. Create a frame variable called number of swaps, type size t. If you do a swap over here, number of swaps plus plus, number of swaps plus plus. Same thing over here, return number of swaps made. That's it, game over. So here into the frame variable called number of swaps, I do not show it here, but you understand what's going on. I receive the return value of the sort A routine, address of A, address of B, address of C, and once that call is made, you craft the printf statement accordingly. After, you will say it like this: after %zu swap sort, the integers look as follows. This is the specification for size t, unsigned integer. That is the entire processor size, wide 64-bit, wide 8-byte unsigned integer. And this is basically game over. Create the variables, print them before, sort them, capture the number of swaps that were actually carried out physically over here, and print all this information out. Game over. Feel free to experiment with this code on your own. Meanwhile, we will move on to a comparison of this creative algorithm versus its non-creative counterpart. When we compare the time complexity, so to speak, of a creative sort versus non-creative sort, then we see that with the creative sort shown on the right-hand side of your screen, we perform exactly 1, 2, 3. We perform 3 tests of the values that sit in our integers. And in the non-creative brute force zero intellectual effort algorithm that we came up with right away, we perform 12 tests. So evidently, 3 is much better than 12, 4 times better as a matter of fact. And if we decide to drill down a little bit and include the cost of swapping the material that is passed into our algorithm, then in our traditional straightforward version of swap, how many assignments do we have? 3. So for each test over here, in the worst case scenario, we have what? 3, 3 plus 1, 4, 4 times 3. On this side over here, the net cost will be 12 operations in this case. That is comparisons and assignments. But in the non-creative algorithm, we had 12 comparisons alone. And we remember that that algorithm does not actually sort the input material at all. It just displays the variables that were passed in a order that was requested in an ascending order, but it doesn't actually sort anything. So this algorithm is not only uh, uh, inefficient, it is also not practical. So if we decide to actually sort the input material in the non-creative version of the algorithm, we will definitely do more than 12. So in this case, the sum total will be still greater than 12. So the number of steps over here will be greater than 12, larger than 12. I'm sorry, we should say larger than 12. There will be over here some number of steps, and that way the non-creative algorithm for sorting 3 integers will still be less efficient than our algorithm that either takes 3 comparisons or 12 operations in total versus 12 comparisons and who knows how many more total operations if that algorithm was to sort the integers actually. Now that we're done with the sorting, with the problem of sorting 3 integers, we can take it further. And here, as it is traditional in the world of computer science algorithms, we can go deep or we can go wide. Going with our algorithm deep means increasing the number of integers that we have to sort creatively. And the next number on the menu is 4. How do we creatively sort 4 integers? Where here I reflected this change in our algorithm. In the signature, we add one more argument. Over here, we erase C. We turn this into a comma. So the address of another integer d is coming into our sorting algorithm. What does change substantially, if at all? Well, again, we do here when we take on the 4 integer sort problem in computer science, we do to that problem the same thing we do to similar problems in mathematics. If we are given the integers, let's say a, b, c, and d, what do we do again here? Well, the same thing that we did previously when we stepped up from the 2 integer sort into the 3 integer sort. Here we capitalize on the fact that we already know how to solve a smaller problem, a 3-integer sort, which we saw in the previous segment. So we sort first, we sort 3 integers creatively, and we know we can do that in the minimal number of tests. Instead of 12, we do it in 3. 1, 2, 3, and this sorting process is still is where it was. I kept it on the same side over here, but now we jump to the extension. So here we jump from here to this side on the board to see what will we do with the 4th integer. Well, if we sorted the integers A, B, C correctly, so we have A is less than or equal to B, which is less than or equal to C. That much our code over here guarantees. Now we have to place the 4th coin, let's say. You see again, here I interchangeably use coins and integers back and forth. In my mind, this is one and the same thing. So, and that is probably a sign that this reinterpretation was successful. So what are the choices here? Well, D can go to the left of A, D can go to the right of C. It can also it can sneak in between B and C and between A and B. So in this case, evidently when the number of choices is odd, what is the winning scenario over here? What do you guys think? Put this video on pause, walk away, think on your own, come back. The idea here, my idea here, for example, is to fight it out against the middle coin, the integer in the middle. And that is reflected in this test over here. We compare this integer D with B. Why is that? Well, when we compare the integer D with the integer B, in that case, we can either go left towards the lighter coin or smaller integer, or we can go right towards the heavier coin so far in the set. The lightest coin in the set so far, the heaviest coin in the set so far. The smallest integer in the set, the largest integer in the set. And if any of these tests do trigger, what do we do? Well, the same idea that we discovered when we were solving the rock bottom simplest problem. Test and rename, test and swap if needed. If the integer D is larger than B, then we need to sort it against the integer C. And how do we do it? Well, the same maneuver. If C is larger than D, we swap C and D. If D is not larger than B, then we come over here, and if A is larger than D, so if A is larger than D and D wants to be over here on the left side of A, then we swap A and D. We swap A and D, and this is over. The game is over. To save you guys some time, I will not be going into sample computations, but take, for example, integers. For example, the same ones that we used in the previous set: 9, 7, 5, and 3. Evidently, after that sort is carried out, we should have the integers positioned which way? In an ascending order. 3, 5, 7, 9. Right, construct the same table, see how the numbers dance. Examine, analyze the time evolution of this algorithm, see how the numbers perform, play with different numbers, prove to yourself that this algorithm works. But the bottom line is what? How many tests do we do in this case? Well, we still do 3 tests from sorting the 3 integers creatively. And in order to place the 4th one, we need to carry out this test. We need to pit the D coin against the B, the middle coin over here, the middle integer. So this is the test. So 3 plus 1 is 4. Let's write it down. 3 plus 1. And now once we branch over here, how many tests we have? Well, 1 here or 1 here, either way. So far so good. So plus 1 more. So this is a total of 5. So 4 coins, A, B, C, D, can be sorted creatively in an ascending order in 5 tests, 5 comparisons shown over here. This is the algorithm, and again, you can experiment with tracing the time evolution of this sorting algorithm on your own. But here we will take this idea further and see how or what the analysis and the tracing of the algorithm as a time evolution of numbers as they jump around, what it can lead to. We're all wired differently. We all think differently, and that is a good thing. And for full record and a full disclosure, I personally do not really know how the people who actually came up with the formal notion did come up with it historically and in real time. But in this episode, I try to present a plausible way of how these things may come about. Because remember, if you go back to our analysis of time evolution of how numbers jump around through our sorting algorithm, it is actually not too far-fetched, and perhaps it will happen almost by itself that we will at some point realize, aha, we do not really need to um, draw all these elaborate tables that we did draw. A much more sanitized construct that is uh, totally separated from all sorts of context and only captures what we're trying to do in a very formal way is enough. And this construct is known as sorting networks. And the idea behind the sorting network is to precisely that, to capture a way in which some number of inputs can be sorted without the traditional, so to speak, industrial strength sorting algorithm, bubble sort, heap sort, quick sort, this and that, all sorts of sorts. And in some sense, how these inputs can be sorted manually by hand, but still with the requirement that the number of tests must be minimal. So here is a sorting network for 3 inputs. These white lines are called wires, for example. And again, I'm not going to bore you guys with all the details. You can study this on your own. Once you make a discovery, then here another entire sub layer in computer science is born that deals precisely with sorting networks. Here is a sorting network for 3 inputs, and you can see that it's quite transparent that first we compare our coins in our integers a and b, a and c, and then c and b, or b and c, and then on the output over here on that side, the input will be sorted in precisely the way we want. So here the blue lines represent what? The blue lines represent exactly test and switch if you have to accordingly. So here again we can draw the values, for example, pump 3 integers through this sorting network. Again, draw our outcomes, flip this, flip that, and then see what happens on the other side. This is a fun exercise, and you guys should do it on your own. But the idea is that the moment we make this discovery, the race for the academical discipline is on, because now we have to generate a proof that our sorting network is correct. That is a challenge. That is an interesting thing to do. Then we have to do the other interesting and challenging thing is to invent a way to put this sorting networks together when the number of inputs becomes larger and larger. For example, we saw that with 4 inputs we can sort them creatively in how many tests? With 5 tests. And if we have 5 inputs, then it is evident that we can do it in no more than 9 tests. But if the number of inputs becomes larger and larger, 6, 7, 8, 9, 10, 15, 29, 32, for example, then that already gets quite interesting. How do we prove? This is where the idea that we need a way to prove that these things are correct. How do we prove that our, for example, 32 input sorting network is correct? So this was the purpose of this episode, was to show a plausible way. Again, just make sure that you guys understand, I'm not claiming that this is how sorting networks were discovered. I'm not really sure if anyone in our community knows the historical real-time development. Please share with us in the comment section. But this is a plausible way how a discovery, a meaningful technical discovery, can be made. And now, instead of going deep, we will discuss shortly what we can do if we go wide. Instead of doing depth first and doing width first, in our case, in our particular context, means that instead of increasing the number of inputs into our sorting algorithm, we want to expand the amount of material or the width of the material that can be sorted in a meaningful and a sensible way. And if we go back to our implementation, then we will see that the function that we refer to as swap is very hardwired to deal with integers. The sorting routine is hardwired to deal with integers as well. And again, in a professional setting, this will not be acceptable. And as an extra for experts, this segment is not for everyone. You can skip this segment and couple next ones and go to the next challenge. But for the curious travelers, here is the situation. We can do this. We can increase the amount of material that can be sorted in a sensible and a meaningful way, of course, by using a comparing or a comparison predicate, if you will, in high tongue, or we introduce in C programming language by the means of type def, we introduce a basically pointer to a function that returns integer. We will name this pointer to a function larger than comparator t, let's say. This is a traditional way, that takes two arguments, and these arguments are separated from the specific types: void pointer to the material that needs to be compared. This time, with this approach, what we can do is we can write as many specific comparators as we like and ship these comparators as a pointer to function as an argument to the sorting routine. I will talk about it in a second, but the idea here is that we can write, for example, a routine, a comparator that will sort integers, that will sort floating point numbers, that will sort, for example, strings, a comparator that will sort or compare, I don't know, IP addresses. If you think that you can compare two IP addresses in a meaningful way, then you can do that. And here there is a small caveat, and the way you will sort with the comparator routine will be as follows. When we abstract our comparison process and separate or detach that comparison from a specific data type by the means of the introduction of the comparator function or a comparator predicate, if you will, then one detail that we should keep in mind is the following. Our swap function, instead of dealing with the pointer to, should really deal with the pointer to, because the side effect of that approach is the fact that the swapping routine can be implemented in terms of manipulating addresses and not knowing anything about the underlying data types. We simply swap addresses. Here, again, do realize that the arguments now are pointer to, reflected with 2 stars over here and 2 stars over here. Then our temp variable becomes a opaque or generic pointer to. We store in it the address, for example, that comes in X. We swap these addresses as shown over here and move on. Game over. We write this function once and we don't have to come back to it again. Our sorting algorithm, our sorting function over here, will also have to operate in terms of pointer to, two levels of indirection. So the argument, the signature of our function changes, void star star. uppercase A void star star, uppercase B void star star, uppercase C, where ABC now stands for literally anything that you uh, care to compare, or literally anything that can be compared in a sensible and a meaningful way. And the fourth argument now will be precisely the comparator of type pointer 2. And here I call it larger than. The if statement will be then crafted if larger than star A star B, because now this comparison, I'll show how it works in a second for example, for comparing integers. If that comparator returns true, then we perform the swap. Swap takes A and B, void star star, void star star, comes back over here. The circuit closes, game over, we're home free. That way we can write this code once, and then we can go to town on different types of comparators, like I said before, and instead of duplicating this code over and over, duplicating the swap function, duplicating the sort function, we have only one copy of swap, only one copy of sort, and then as many comparators as we care to meaningfully and sensibly put together. And there will be one little caveat in how we use this, and I will show it to you in the next segment. And when you put all these moving pieces together into one executable package, then it can be done as follows. For example, the comparator for integers is implemented in pretty much the same way, except that the signature of this comparator has to conform to the signature of what we defined earlier. So it has to be void star A, void star B. And then the first thing we do is we cast the incoming pointers into pointers to integers. And then again, if the first argument is larger than the second one, then we return 1. Otherwise, we return 0 and game over. This is all there is to it. Now, the one important detail to keep in mind when you already start exercising this functionality for real, so to speak, then yes, you create a frame variable called A. You initialize it from the command line argument, argv0, a to I, ASCII to integer. This is a standard C runtime library function. All the includes are in my free PDF file. Do not worry if you do not catch any of the details. All the details are in the file available to you. You can take as much time as you need to study this. Here's the thing. We also create another frame variable for each integer, which is of type what? Which type? Type pointer to an integer. You see, pointer to an integer, we initialize it with the address of this frame variable. And we do so for all the other ones, P, B, and C. Now, before we print these guys, we can actually use these guys as well, but just to show you the delicate difference is that when we print the values of the not sorted integers, it's okay to use A right away, A, B, and C. Now, when we invoke our sorting routine, when we invoke our creative sorting algorithm, what we pass into it is the address of this variable. So this becomes a pointer to a pointer. Address of pointer to a variable B, and address of the variable that stores an address of variable C. And our integer, this guy right here, this guy, is the integer comparator. That's it, game over. Once that function comes back, it does its thing, it sorts the integers. What we do over here in the printf, that's the important detail I showed to you in blue, guys. Here we dereference the pointers that are stored in these variables, PA, PB, and PC, because the addresses to which these guys point, these guys can shuffle. They can point to B or C, however it may happen inside that routine with the swap function, which I showed earlier. And this is pretty much it for the problem S3CS1. If you have any questions, use the comments below. Again, do not worry if you did not catch some details, even for like let's say beginners and even intermediate C users, this will be quite challenging. This is more difficult material than usual. However, in the professional environment, in the production code, this is exactly what I would do. I will fix everything that can be fixed and written once, the swap and the core sorting routine, and only vary the small pieces that must be varied, and that is the specific comparators for integers, doubles, floats, strings, IP addresses, what have you. So this is it for the uh, problem S3 CS1, and we will move on to a new challenge next. Our next challenge will be a problem in mathematics, and in our nomenclature it will be the math problem S3M5, shown over here in the upper left hand side of the board on your screen. But in reality, this problem comes from an absolutely wonderful book called Hungarian Problem Book number 1. This is a problem for those who have this book. This is a collection of problems that were given in Hungary between the years 1894 and 1905, based on, I'm not sure if I should even venture to pronounce this, Yotvosh competitions. If someone knows how to pronounce it better or the correct way, let us know. And for those who have this book, we will be solving the problem number 2 from the competition that took place in the year of 1895. This is at the bottom of page number 9. These problems look as follows. They are listed on a small number of pages. Again, this is what the book looks in the front. This is what the book looks like at the end. Again, I'm not going to venture to pronounce the name of this gentleman. Maybe I should try. Joseph Gershak. This gentleman has an absolutely, or had an absolutely immaculate mathematical taste. The book is absolutely wonderful, highly recommended. So the challenge in this competition is the following. Given a right triangle ABC, the magnitude of whose interior angle at B is precisely pi over 2 radians. The triangle ABC is such that the angle B, ABC, the angle B is pi over 2 radians. The interior angle at B is right. Find or construct, actually we want the construction steps, construct the point N inside the triangle. The point N should be located inside the triangle such that the magnitudes of the angles NAB, NBC, and CA all equal one another, as shown over here. Again, just to make sure that we're all on the same page. This is problem number 2, given at the bottom of the page number 9 of the competition, Hungarian competition 1895, in the book that I just showed you guys. And the names of the vertices of the right triangle in this case are given over here in the counterclockwise, or as we say in complex analysis, in the positive direction. A, B, C. In other words, if we walk the periphery of this triangle from A to B, from B to C, and from C to A, our left hand will always be inside in the innards of the triangle. Our right hand will be outside. The magnitude of the interior angle at B is right. Construct, describe the sequence of steps with the Euclidean tools alone, with the straight edge or unmarked ruler and the compass, that will locate inside the triangle the point N such that the magnitudes of the angles NAB, NB, CE, and CA all equal one another. And it is very straightforward to understand how this naming of the angles takes place. If our names of the vertices of our right triangle are in the counterclockwise fashion, then in exactly the same fashion we'll look from the point N into the angles, and then we move counterclockwise again, standing at the point N, looking at A. The next maneuver is to go to B, so the angle is NAB, NAB. Turn, still standing at N, looking at B. The next angle, the next vertex will be C, so the angle is NBC, NBC. Turn, standing at the point A, looking at the point C. The next one will be A, so the name of the angle is NCA. Good luck. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share with you my solution of the mathematical problem S3 and 5.